So we are going to start with this topic, capacitance of a parallel plate capacitor with the dielectric slab. We already know that the capacitance of a parallel plate capacitor is C is equal to epsilon naught A over D. This we already know. So now what we are going to do is to insert a dielectric slab between the plate of capacitor. Assume that this is the plate of capacitor. These are the two plates of capacitor, and positive charge is here, negative charge is here, and the electric field between the plate, that you already know that the electric field between the plate is E is equal to sigma over epsilon naught. This you already know. So let this value be E naught. That is the electric field between the plate of the capacitor. Now I'm going to put a dielectric slab into the space, but the slab is not going to cover the whole of the volume. It's not going to cover the whole space. Okay. So the thickness of the slab is T. T is the thickness of the slab, and D is the distance between the plate. D. So T is the thickness of the slab, and D is the distance between the plate. Now, if you look closely, in this region, there is no dielectric. In this region, there is no dielectric. Here also, there is no dielectric. So if there is no dielectric in this particular region, then here the electric field is still going to be E naught. But in this region, there is a dielectric here. So here the electric field is not going to be E naught. It's going to be E naught minus EP. Now what is E naught minus EP? If you do remember about dielectrics, we have done this before, that in dielectric, the electric field, the net electric field in a dielectric is E naught minus EP. E naught minus EP. If you don't know this, please go back and see the video, dielectric wala video. You can watch it again, because there is an electric field from outside, E naught, and due to that, there is a charge concentration here, positive, negative charge concentration, and this charge concentration is what we call polarization. And due to this polarization, there is an electric field that is set up, that is what's called EP, electric field due to the polarization. So inside the dielectric, you have an electric field E naught minus EP. Why minus? Because you can see that E naught, that is external electric field, is towards this direction, towards right, and EP, that is electric field set up by the polarization of the charge, is in the opposite direction. So the net electric field inside the dielectric is E naught minus EP. So we are going to use this. We are going to use this E naught minus EP electric field inside the dielectric here. So what we see, that inside the dielectric, the electric field is E naught minus EP, and outside it is still E naught. Still E naught. Now, what are we supposed to find? We are supposed to find capacitance. And you know that capacitance is equal to charge over the potential difference between the plate. Now, what is the potential difference between the plate? Let's find this one out. You know already from this potential gradient formula, E is equal to minus of dV over dr. You know this. Now, what was this formula? Potential gradient. It was to find the potential difference between 2 points. dV is the potential difference between 2 points. That means if we do electric field times the distance between the 2 points, we can find the potential difference between the 2 points. So we are going to use this concept to find the potential difference between the plate. What we do, we want to find, want to find the potential difference between this and this plate. And how are we going to find? We are going to find it by using this concept, E dot D. Now, if you look closely, that the electric field between the plate have value of E naught where there is no dielectric, and a value of E naught minus EP where there is a dielectric. So my potential difference would become E naught times D minus T. Now why D minus T? Because we can see that E naught electric field only exists in this region, only exists in this region. And you can see this region is actually D, the distance between the plate minus the thickness of the dielectric. So this region is D minus T, and plus this electric field that is in the dielectric, that is E naught minus EP, E naught minus EP into T. So this is my potential difference. Now E naught minus EP, E naught minus EP can also be written as D minus T, and E naught minus EP can also be written as E naught by K. Now how did we get that? If you again, if you have gone through the video, dielectric video, so you would know that the dielectric constant K, this is the dielectric constant. Dielectric constant K will be E naught divided by E naught minus EP. Okay, so I can write this as E naught by K is equal to E naught minus EP. Okay, and K again, don't confuse, this is dielectric constant, or this is also called relative permittivity. So the same thing is also written as ER. Okay, so don't get confused. ER and K are the same thing. Relative permittivity, dielectric constant. So we are going to use this. So here E naught minus EP, this value here will then become E naught by K. E naught by K into T. That means potential difference, I can take this E naught and this E naught, these two as common, and I will get E naught into D minus T plus T over K. Now, we know that the electric field between the plate is sigma over epsilon naught. We know that, and this we can again, sigma we can change into charge over area and then epsilon naught. So again, here we see that E naught can be written as charge over area. This charge over area has come from this sigma, surface charge density. And then our potential difference will become Q by epsilon naught A D minus T plus T over K. Now, what did we wanted to find? What we intended to find? We wanted to find capacitance, isn't it? So capacitance is equal to what? Charge over potential difference. Now, potential difference is this value, this whole thing. So I'm going to put this whole thing in the denominator here. So it will become Q by epsilon naught A T minus T plus T over K. So this Q will cancel and this will come on the numerator. This will come on the numerator. So you are going to get C is equal to epsilon naught A divided by T minus T plus T over K. Okay, pretty simple. So we got the value of capacitance when a dielectric slab is inserted. Value of capacitance when the dielectric slab is inserted. Please do this derivation nicely. This is a CBSE and a PU standard derivation. Okay, this value here. Now we have got this value of capacitance epsilon naught A by D minus T plus T by K. Now we are going to do some special cases here. Special case means, let's say we put a dielectric, but this time the dielectric is not occupying a small space, but it is occupying the whole space. That's mean something like this. You have this as a capacitor plate, and your dielectric is occupying the whole space. The whole space is occupied by the dielectric. Okay. Now, if the whole space is occupied by the dielectric, then the thickness of the dielectric will be is equal to D. Thickness of the dielectric will be is equal to D. Now, if T is equal to D, then what will happen to this formula? This value, D minus T, will become 0 because T is equal to D. T is equal to D. That means your capacitance will now become epsilon naught A. D minus T has already become 0 divided by T. Now T, I can write it as again D because T and D are same as dielectric is occupying the whole space. So I can write this as D by K. Now this K will come on top. That means this will become K times. It will become K times. So the capacitance will then become K times the original capacitance, epsilon naught A by D. Now, according to this, you can again define the dielectric constant. You can again define the dielectric constant because here, as you can see, the dielectric constant K can again be written as the capacitance after inserting the dielectric divided by the capacitance before inserting the dielectric. So we can see that the capacitance of a parallel plate capacitor increases K times. You see, it increases K times when its entire space is filled with dielectric material. And then dielectric constant can also be written as capacitance with the dielectric between the two plates. That is this value, capacitance when the dielectric is inserted between the two plates, divided by the capacitance with vacuum between the two plates. That is this value, C naught. Okay. So the dielectric constant of a dielectric material may be defined as the ratio of the capacitance of the capacitor completely filled with that material to the capacitance of the same capacitor when vacuum between the plates. Now, this is not the standard definition of dielectric. So don't write this definition in any of your exam. This is not the standard definition. Standard definition of dielectric has been discussed before. This is just the definition or explanation of the dielectric with respect to this formula. Now the next topic is capacitance of the parallel plate capacitor again, but this time with a conducting slab. So previously we did capacitance with the dielectric, okay, with the dielectric slab, and now we are going to do with this conducting slab. Now you already know from the concept of dielectrics and conductors, like how dielectric behave and how a conductor behave. So you know that in a conductor, the electric field inside the conductor is actually zero. Inside the conductor, the electric field becomes zero. This you know from multiple concepts. The first chapter, Gauss's theorem, and this dielectric conducting, how the behavior of this dielectric and conductors. You already know this. Inside because of very high polarization within the conductor, because conductor do allow flow of charge, you know that because of very high polarization, the electric field that is set up due to the polarization, that is EP, is very large. So this electric field that is set up inside is EP, and this outside is E naught. Inside the conductor, EP, that is electric field due to the polarization, is equal to E naught, and that's why EP minus E naught is equal to 0. Now, you know that the dielectric constant K is equal to E naught divided by E naught minus EP. because for the conductor, this whole value becomes 0, E naught minus EP, E naught minus EP will become 0. So then this thing in the denominator, this becomes 0. As this whole thing becomes 0, so what will happen? This K, that is a dielectric constant, will become infinity. Now, if the dielectric constant become infinity, what was our capacitance formula that we found out here? The capacitance formula we found out here. You see this formula here. Epsilon naught A over D minus T plus T by K. So we are going to use the same formula. Epsilon naught A divided by D minus T plus T over K. Now T over K we just have found out that for conductor the K value is infinite. That means T over infinite, this value will then become what? 0. This whole thing will become 0. So your capacitance value will simply become epsilon naught A D minus T for a conductor. So if we insert a conductor between the plate of capacitor, if we insert a conductor between the plate of capacitor, then in that case, my capacitance value will be epsilon naught A D minus T. Now you can change this formula a bit. As you can see, capacitance is equal to Q by V, that is epsilon naught A by D minus T. Then you can multiply and divide this expression with D. So if you do so, divide by D, multiply by D, and epsilon naught A by D, here you will get this. This was the original capacitance. Original capacitance means when vacuum was filled between the plate, when no conducting slab was between the plate, when vacuum was there, in that case the capacitance was epsilon naught A by D. That means my capacitance after filling the conductor C is equal to D over D minus T times the capacitance with vacuum filled between the plate. So C is equal to D over D minus T times C naught. So thus the introduction of conducting slab of thickness T in the parallel plate capacitor increases its capacitance by the factor of D over D minus T. So we are going to understand the series and parallel arrangement. Okay, series and parallel type arrangement of dielectric. That means the dielectric can also be arranged like series or parallel within the plate of capacitor. How will you identify that? How are you going to identify that? So this is the series arrangement. This is the series arrangement. Now how to identify that? You see, when you did the capacitor in series and parallel, what did I taught you? I taught you that the capacitor's plate are connected to each other. The capacitor's plate are not all connected to the cell. They are connected to each other. Here you see the same logic applies. You see this dielectric. This dielectric is not connected to the plate here, or it's not connected to the plate here. It is actually connected to the other dielectric. And the same goes with this one also, because this is only connected with one of the plate, and this is also connected with one of the plate. That means dielectric are connected to each other, not individually connected to the plate of the capacitor. So this becomes the series arrangement. Whereas this one, you see, this will become a parallel arrangement. Why? Because you see, each dielectric is directly connected to the plate of the capacitors, both the plate of the capacitor. The red one is also connected to both the plate, blue and green, both of them are also connected to both the plate of capacitor. So this is a parallel type arrangement. You need to first identify what kind of arrangement it is. Okay, then only you can apply some formula, some concept and solve it. If you fail to identify this, is it series or parallel, you will get it wrong. Do not always follow the diagram. You may see the diagram differently. So many students make a mistake here. For example, if I make the capacitor plate like this, okay, if I make a capacitor plate like this, and then I put the dielectric like this, Now you try to identify whether this is a series or a parallel combination. What is this? Is it series or it is parallel? So here you see the three dielectrics are directly connected to the plates of the capacitor. That means this becomes a parallel connection. Okay, this becomes a parallel connection. So please don't follow the diagram quickly. First identify the arrangement with this concept that whether they are connected to each other or they are connected to the plates of the capacitor. That's how you identify whether it's a series or a parallel arrangement of dielectrics. Now, if you do have a series arrangement, then what will happen to your what will happen to the now for the series type, as you can see, this is a series type. So for the series type, what happens is that individual dielectric is K1, K2, K3, and the thickness of this slab is T1, T2, T3. Now, our original formula that we derived for this dielectric type was epsilon naught A by D minus T plus T by K. But when we derived this formula, we did it for one single slab, isn't it? One single slab having a thickness T. But now that we have multiple slabs, so our formula would change a bit and it will become like this. Look closely. Epsilon naught A, this remains as it is on the numerator, and in the denominator, because you have multiple slabs, so you will have D minus of this T1 plus T2 plus T3 till Tn, the number of slabs that you have. Because you have multiple slabs, so the thickness of T1, T2, T3 all are taken into here. Plus T by K. Our original formula has this T by K. Again, we have multiple slabs here. So it will become T1 by K1 for the first slab. So the second slab and so on for the Tn by Kn. But as we see in our in our diagram here, that the slabs are occupying the entire space between the plate. Okay, entire space. You see all the slabs are occupying the total space between the plate. That means the sum of the thickness T1 plus T2 plus T3, this all will become D. They will all combine to become D. So this T1, T2, T3, they all will combine to become T. And if they all become T, that means this quantity here will become 0. Okay, this will become 0. And then our formula will become epsilon naught A divided by T1 by K1, T2 by K2, and keep on adding up like this. This is for the series type arrangement of dielectric. Now for the parallel type arrangement, you first need to understand that in a parallel arrangement, these slabs are actually touching both the plate of the capacitor. That means that the thickness of all the slab is T. Okay, the thickness of all the slabs is T. In the series type, in the previous case series type, the thickness of the slab was T1, T2, T3 because they were not covering the whole space. They were covering a small space between the plate. But in the parallel type, you see that each slab is having a thickness T. But all the slabs does not cover the whole area of the plate. See, they cover the distance between the plate, but not the area of a plate. That means this slab would cover an area A1, this slab would cover an area A2, this slab would cover an area A3, like that. Now, a simplified diagram for this may also look like this. You see, I can consider these three slabs behaving like three parallel capacitors. These three slabs would behave like three parallel capacitors having these slabs, having this dielectric slab between them. So these three slabs would behave like three parallel capacitors having this dielectric. Now this capacitor having this dielectric, this capacitance would then becomes the dielectric constant of this, that is K1. Okay, assuming this is K1, and K1 then epsilon naught, then A1, because as I said, the area that is covered by individual slab between the plate is not same, they are different. Okay, so it will become A1 and divided by the D, the distance between the plate, because the individual dielectric is covering the whole distance. Individual dielectric is actually covering the whole distance, but not the whole area. So I have A1 by D. Okay, K1 epsilon naught A1 by D. Again, for this one, it will become K2 epsilon naught A2 by D. This will become K3 epsilon naught A3 by D, whatever be the area. So like that you have to calculate. But as we know that they are in parallel, so eventually the equivalent capacitance, if you calculate, it will become what? It will become C1 plus C2 plus C3. That means this one plus this one plus this one. Eventually you are going to get a formula like this. Just hold on. You see, you will get a formula as C1 plus C2 plus C3 till Cn, and individual C, the C1 will be is equal to K1 epsilon naught A1 by D, then K2 epsilon naught A2 by D, then Kn, and so on goes. So epsilon naught by D, this value is a constant. You see, it's there in every term. So that's why I can take this as a common term here, and then I will get K1 A1 plus K2 A2 and so on. Okay, so this is our simplified formula. Now, if at all the area A1 is equal to A2 is equal to A2, A3, this is a condition. It's a condition where the area covered by the individual slab, let's say this area. So this area is equal to this area is equal to this area. That means A1 is equal to A2 is equal to A3. If that is a condition, then A1 is equal to A2 is equal to, then the individual area would become A over N. N is the number of slab. And then my formula would become something like this. But mind it, this is just a condition in which A1, A2, A3 all are same. If this is not same, then this will be your final formula to use.